Hello, my name is Marcos Maroñas, and I am going to present you our work titled Evaluating Work-Sharing Tasks on Distributed Environments. This is the outline of the presentation. I will start with an introduction, then I will give some background about TAMPI and work-sharing tasks. After that, why we think using work-sharing tasks and TAMPI in distributed environments is a good approach. Then, an analysis and evaluation of LULESH and HPCCG, and finally, conclusions and future work. So let's start with the introduction. In this work, we focus on hybrid programming, concretely MPI plus tasking. MPI is used to manage the inter-node parallelism, while tasking handles the intra-node parallelism. As a result, we obtain low latency communication and high throughput from the MPI side, and from the tasking side, we obtain a flexible data flow execution model, an inherent ability to overlap communication and computation, and also a natural ability to cope with intra-node load imbalance. Nevertheless, the combination of MPI and tasking still presents some challenges, like possible deadlocks if MPI calls are not properly placed, and increased communication overhead in case tasks are blocked waiting for communication, and task granularity issues. Our proposal includes the use of the Task-Aware MPI library, also known as TAMPI, to prevent the deadlocks and communication issues. Additionally, the use of work-sharing tasks helps us to mitigate the task granularity issues. Let me introduce TAMPI and work-sharing tasks to understand why they can help us to overcome the mentioned challenges. TAMPI is a library that simplifies the combination of MPI with other programming models such as OpenMP or OpenMP+X. It sits between the application and the programming model's runtime libraries, as shown in the figure on the bottom. TAMPI guarantees that no deadlocks will appear even though MPI calls are placed within tasks. Additionally, it removes artificial dependencies and enables the natural overlap of computation and communication. TAMPI has two different modes, blocking and non-blocking. In this work, we only use the non-blocking mode, so I will just introduce the non-blocking one. The figure on the right shows the different states a task can reach. After creation, it becomes blocked until the dependencies are satisfied. Then, it becomes ready, and eventually, it's scheduled for execution. While running, a task can be paused. When a task finishes to run its code, it is finished. Finally, after releasing its dependencies, it is complete. We can see in the slide a code with two tasks. The first task contains an MPI IReceive that writes data in a buffer that is later read by the second task. Also, in the code, we can see that the first task specifies output dependencies over two variables that are input dependencies of the second task. As a result, the second task cannot start until the first one completes. Using regular MPI, we would have to place an MPI wait in the second task to wait for the IReceive to finish. Thus, the task would become paused and the core running the task would become idle while maybe other tasks are ready to run. In the case of the code shown in the slide, the first task finishes after the TAMPI iWait all, but not completes, meaning that the dependencies are not released and the second task cannot start yet. As a result, the core can get other ready tasks and keep progressing instead of being idle waiting for the communication to complete. Work-sharing tasks are a special kind of tasks that can be run by several cores concurrently using work-sharing techniques. It can only be used in for loops where the iteration space is partitioned into chunks that are later distributed among threads. It behaves like a regular task in every other aspect. In the slide, we have a sample code parallelized using regular tasks in the top, using OpenMP work-sharings in the center, and using work-sharing tasks in the bottom. In the case of tasks, we see that there is not enough parallelism, and the CPU usage is not optimal. In the case of work sharings, there is load imbalance. This, combined with the barrier at the end of each work sharing, causes also as optimal CPU usage. Using work sharing tasks, there is a two-level partitioning that prevents the lack of parallelism of regular tasks. Additionally, as it introduces no barrier because the synchronization is done using data dependencies, the load imbalance is not a problem because as soon as a chunk finishes, another starts, even if it belongs to a different work-sharing task. As a result, we have a better CPU usage that can enhance performance in some scenarios. So, let's see how the use of work-sharing tasks and TAMPI can help us to overcome the challenges presented in the introduction. The granularity tuning is a challenge inherent to the use of tasks. Tasks are more flexible than work sharings, but the management of tasks introduce overheads that are not negligible. The task management overheads are determined by the runtime library. Also, to achieve an optimal utilization of the resources, there must be at least one task per core. Otherwise, there is lack of parallelism. So, if we use a very fine granularity, task management overheads hurt performance. However, if we use a very coarse granularity, there is lack of parallelism that also hurts performance. We can see that in the chart, which shows granularity in the x-axis and performance in the y-axis. In phase 1, there is too much overhead and we cannot reach peak performance, while in phase 3, there is not enough parallelism and we cannot reach peak performance neither. In phase 2, the granularity is optimal and we can actually obtain the peak performance. In the chart, there are also 3 different series that represent different problem sizes. It is possible to see that the green series is never able to reach phase 2. This is because there is a further factor to consider when tuning task granularity, the problem size. In the case of the green series, the problem size is so small that when tasks are coarse enough to stop suffering from task management overheads, there are not enough tasks to fit all the cores, so that peak performance is never reached. When doing strong scaling experiments, there is a fixed problem size while the number of cores keep increasing. As a result, we may end up in a scenario like the one in the green series. The problem size is so small that we cannot set an optimal granularity. Using work-sharing tasks, a single task can fit multiple cores. Thus, we can set coarser granularities without incurring in lack of parallelism, enabling us to reach peak performance. So, the use of work-sharing tasks enable us to mitigate task granularity issues. Let's see now how we can deal with the possible deadlocks. In the code of the slide, we show an example of such a situation. If we run this code with a single thread per process, all the processes will block in the MPI receive, and none of them will ever perform the MPI send. With TAMPI, this does not happen because when the first task finishes its code, it goes ahead and starts running the next one. Also thanks to TAMPI, we can deal with the increased communication overhead. In the sample code, we have 2 ready tasks, task A with an MPI call and task B with some compute. Using regular MPI, when a core requests work, it is assigned task A that may become blocked waiting for the communication to complete, wasting CPU time. When the communication completes, the task unblocks and completes, and B can run and complete. With TAMPI, the core also starts running task A, but when it becomes blocked, it releases the core, and it can run task B while the communication completes. Then, it gets back task A and completes it, overall saving some time. We have evaluated our proposal of using work-sharing tasks and TAMPI in 2 different applications, LULESH and HPCCG. LULESH is an application with 2 different main phases, one devoted to perform operations over elements and the other one devoted to perform operations over nodes. There are several different kernels with very different computational costs. It has a high degree of parallelism and presents load imbalance problems. In the slide, we can see an execution trace of LULESH. In the y-axis, we have different cores used in the execution, and the x-axis shows the time. The trace shows what's doing each core at any moment. White color means the core is idle, while any other color means it is running a task. Each color represents a different task type. On top of the trace, we can see 2 arrows specifying the different phases of the application. Also, in the bottom, we have 4 different arrows specifying where are the communications. This trace is taken from an execution with a big problem size and a single granularity for all the different task types. It shows a single iteration of the application. We can see that it behaves reasonably good with very few white color, meaning that most of the time the cores are running tasks. However, if we reduce the problem size to make it closer to strong scaling scenario, the trace looks worse than the previous. Most of the trace shows white color, meaning that the cores are idle. To improve the behavior of the previous trace, we applied some optimizations. Firstly, we tuned the granularity. Then, we used work-sharing tasks in some of the kernels. And finally, we used work-sharing tasks wherever possible. This resulted in 3 different versions, T, TF, and TF-new. In the chart, we see a granularity analysis for each of the versions. We can see that TF-new is the best version, significantly outperforming the other 2, while the T version is the worst. Using the TF-new version of the previous slide, we run again the scenario of the previous trace, which was using a small problem size. We can see that this new version using work-sharing tasks behaves much better, being very similar to the first of the traces that was taken using a big problem size. We see very few white color, so that the CPU utilization is quite good. So, once we got an optimized version of LULESH using work-sharing tasks, which is the TF version, we compared it to the version using regular tasks, which is the T version, a version using OpenMP Worksharings plus MPI, which is the OMP version, and a pure MPI version. We did 2 experiments, strong scaling and weak scaling. In this slide, we show the strong scaling one, where we can see that work-sharing tasks really make a difference compared to regular tasks and OpenMP Worksharings, being closer and even better in some scenarios than the pure MPI version. In the weak scaling, the TF version is clearly the best. In this case, in contrast with the strong scaling scenario, the T version is noticeably outperforming the OMP version, even reaching the MPI version in the last point. This is because this weak scaling experiment uses a big problem size that mitigates granularity issues. Let's see now the evaluation of the HPCCG. HPCCG is simpler than LULESH. It contains a single phase with 3 kernels. It presents a 4-join pattern, so it is very well suited for OpenMP worksharings. We start again with an execution trace of a single iteration using a big problem size. There is a single granularity for all the different kernels. Again, there is very few white color, meaning that most of the time the cores are running tasks. However, again, if we try to reduce the problem size to simulate the strong scaling scenario, things get worse. A lot of white color appears, so cores are idle a significant amount of time. We applied 3 different optimizations. Granularity tuning, which is the T version, the use of work-sharing tasks wherever possible, which is the TF version, and tuning the chunk size of work-sharing tasks, which is the TF-CS version. For the HPCCG, we see no important differences between the peak performance of the different versions. However, the TF and TF-CS versions are able to reach the peak performance with coarser granularities, and this is important for the strong scaling scenario. We repeated the previous trace using a small problem size with the most optimized version. It looks better now, although there is still quite a few white color. Nevertheless, most of it is caused by the 4-join pattern of the application that can be clearly seen in this trace. In the left part, the small orange and cyan tasks are closing parallelism, while on the right part, the small green and pink tasks are closing the parallelism again. As with LULESH, we did 2 experiments, strong scaling and weak scaling. In this slide, we show the results of the strong scaling. We see that all versions perform very similarly up to 3K cores. On that point, the MPI version cannot keep running because the mesh cannot be further split in more MPI processes. Regarding T version, it becomes worse than TF and OMP versions. Finally, in the last point, both TF and T versions stop scaling while OMP keeps doing so. This is because with such a number of cores, the problem size per core is so small that it fits in cache, and the OMP version with static scheduling is able to exploit data locality better. In the weak scaling experiment, as the problem size is big and the T version has no granularity issues, it is able to keep scaling well and slightly outperform the rest of the versions. Nevertheless, all of them perform very similarly in most of the points. So let's conclude and introduce some future work proposals. Throughout this presentation, we have seen that hybrid programming is a promising approach that provides several key features, such as flexible data flow execution model, a natural overlap of computation and communication, and an inherent ability to cope with in-node load imbalance. Nevertheless, it may introduce deadlocks, it may increase communication overhead, and it presents task granularity issues, especially in strong scaling scenarios. We have shown how to overcome or mitigate these problems using TAMPI and worksharing tasks. Our evaluation shown that this is a good approach, reaching up to 1.3x speedup compared to the best state-of-the-art approach, and 3x speedup compared to regular tasks in LULESH, and up to 1.08x speedup compared to the best state-of-the-art approach, and 1.33x speedup compared to regular tasks in HPCCG. In the future, we plan to apply this approach to new applications. As well, we are working on a new construct called Task Loop 4 that eases the use of work-sharing tasks. Finally, we would like to enhance data locality exploitation in work-sharing tasks. So this is the end of the presentation. Thank you very much for your attention, and if you have any doubt, don't hesitate to write me an email to the address shown in the slide.